Okay, so today I'm just going to do practice midterm, which is going to be, so the midterm is this Friday. It's going to be the exact same format and setup as we had before. It's the same setup as the first one. It's going to be available on Canvas for 24 hours. You're going to have like 70 minutes to do it. Maybe I'll just say here, I think the practice midterm is a little more weighted towards sequences than we had before, just because we had less problems about sequences. So I wanted to give you kind of more practice on those. You should think that it's going to be essentially half supremums, infimums, and half sequences. Okay? And you know, this it's not exactly, you shouldn't think every problem, for example, in this section will involve a supremum or infimum. I might put in like a nested interval or something, but that's going to be essentially the setup. In particular, there won't be any, so no proofs from the axioms, okay? So that you can kind of assume on this midterm that, you know, you don't have to prove to me that the square root of x times the square root of x is x, something like that, or negative times a negative is positive. Okay, so I'm just going to go through the midterm, which is in the files part on Canvas. Okay, so for part 1, we had to show that if A is contained in B, then the supremum of A is less than or equal to the supremum of B, and then we needed an example where A is not equal to B. And actually what I meant here, so I think what I meant is A is still contained in B, and A is not equal to B, where the sups are the same. Okay? So I didn't say it maybe the clearest on the midterm, on the practice midterm. Okay, so how do we prove this? Well, we say, again, anytime you want to show that the supremum of a set is less than or equal to something, you have to show that this is just an upper bound for A. Okay? So we claim that sup of B is an upper bound for A since it is an upper bound for B, and A is contained in B. Okay? And that's it. So therefore, by property supremum, we have that the sup A has to be less than or equal to the sup B. All right, and then we need an example where A was contained in but not equal to, and the supremums are the same. So I could take A to be 0, 1, B to be the closed interval at 0, 1. Then the sup A is the sup B, which is 1. Okay? So usually I don't expect, if I'm just saying to give an example, you don't need to provide an argument, but I'm just going to give you a reminder. So if you want to show sup A is 1, follows from, well, 1 is an upper bound. Okay? And for any epsilon greater than 0, there exists R in 0, 1, so that 1 minus epsilon is less than R. Okay? And you can find this explicit R by finding a small 1 over n if you want to make that more precise. Okay, but we've seen that a number of times before, so I won't do it now. Okay, so that's part 1, or question 1. All right, now for question 2, we want to prove that if the supremum of A is not in the set A, then A is infinite. Okay, so there's actually two ways that we can show this. So maybe I'll just give them here. I'll give you both ways. So the first is you can prove the contrapositive. Okay, which just says that if A is finite, then the sup of A is in A. And in this case, this is true because, well, the supremum of A is just the max of the elements A and A. Okay, so it's just the largest element, and in particular, it's inside A. Okay, so you can also show this directly. So let me prove this here. So directly, well, we know, so here's maybe my set A. Again, I don't want to assume it's an interval, so maybe I'll just draw it like here. So this is my set A, looks something like this. Here's the supremum. It's not in A, okay? So we know, say, for every n, there exists an A in A, or maybe I'll call this an A sub n, so that A sub n is greater, so we have sup A minus 1 over n is strictly less than A sub n, which is strictly less than supremum of A. Okay, so since we can find the supremum, we can find these elements that are getting closer and closer to the supremum, okay? And the A sub n are not all the same. In fact, infinitely many of them have to be distinct, right? Because this 1 over n is approaching 0. So if I have, maybe I'll just draw the picture, I have the supremum of A, then I get sup A minus 1 over n. Here I can find sub A sub n. And then, well, I know that here, in between A sub n and sup A, I'm going to be able to find another sup A minus 1 over m, okay? And again, I'll be able to find an A sub m in here. Okay, so these A sub m's are having to not all be the same, so therefore they'll end up being an infinite set. Okay, so let me do part 3, which is going to be pretty quick, I think. So we want to construct a sequence of open intervals A and Bn that intersect in a closed interval. Okay, so again, maybe I'll do some more things, more possibilities here, but just for an explicit example, right, well, we could just look at negative 1 over n, 1 over n. That's perfectly good. Okay, that intersects. So the intersection of these is just 0, which in particular is the closed interval 0 to 0. Okay? Again, if you want to prove this, well, you have to say, well, certainly 0 is inside all of these sets. And as we've seen before, no other real number can be inside this intersection because, well, for any other r and r minus 0, there exists some 1 over n, so that, say, the absolute value of 1 over n is less than r. Oh, okay, that's even silly to say. Oh, I should put it this way, that the absolute value of r is greater than 1 over n. Okay? that will guarantee that it's not in that set. Okay, so some other possibilities, maybe I'll just kind of, if you wanted to say construct an intersection that was half open, so maybe 0 to 1. This is the intersection of 1, negative 1 over n in n. Oops, sorry, this should be open. Okay, so you can make half open intervals, you can make open intervals just by taking the same interval over and over. I won't even, okay, I'll write it. 0, 1 is the intersection of 0, 1. This is a nested sequence of open intervals, just they're all the same. So there are plenty of possibilities that you can construct here. Okay? All right, so let me do number 4, which is you want to show that if xn approaches x and yn approaches y, then xn plus yn goes to x plus y. Okay? Let me bring it up here. So in this case, we'll give the full proof with details. Okay? So we let epsilon greater than 0. We have to show that there exists some n in the natural numbers, so that if n is bigger than or equal to n, xn plus yn minus x plus y, oops, sorry, running out of space, is less than epsilon. Okay? So what we do is, since we had that epsilon, or since xn approached x and yn approached y, we know that there exists some n sub 1 in n, so that xn minus x is less than epsilon for all n greater than or equal to n1, and there exists some n2 in n, so that xn minus x is less than epsilon for all n greater than or equal to n2. Okay? And actually, I think, okay, just to make it a little nicer, I'm going to put epsilons over 2's here. Okay, otherwise I'll get a 2 epsilon in the end. Okay, so therefore, for all n which are greater than or equal to the maximum of n1 and n2, we get that xn plus yn minus x plus y is less than or equal to xn minus x plus yn minus y. Now, by the triangle inequality, we get that this is less than or equal to xn minus x plus yn minus y, which is less than epsilon over 2 plus epsilon over 2, so less than epsilon. Okay? So therefore, this max, which I guess I could have called n3, is the value that we have to choose to get the sum within epsilon. Okay, so let me go to problem 5 now. Okay, so here we had to consider the sequence given by a1 is 7, an is an minus 1 plus 1 over 4 for n greater than or equal to 2. Okay, we had to show this sequence is convergent. And again, so this is an example where, you don't really know what the limit is. Okay, so, and we're also not trying to show that it's a limit, or that we're not trying to show what the limit is, we're just trying to show it converges to something. So this is kind of a hint that you're supposed to use monotone convergence theorem. Okay, so we hope to show that the sequence is monotonic and bounded. Okay, and then we can apply the monotone convergence theorem. All right, so let's try to do this. Okay, so we have, well, first, it's, if you're trying to show it's monotonic, you're trying to show it's increasing or decreasing. So it's helpful to just work out a couple of the first numbers. And then hope that you can show that it's, which one you're supposed to show. So let's just work out A2. Well, this is A1, which is 7 plus 1 over 4, which is 2. A3 is equal to 2 plus 1 over 4, which is 3/4. Okay, so I'm going to guess that it is decreasing. So let's try to show that an is less than or equal to an minus 1. Okay. So writing this out, we get that an is less than or equal to an minus 1 if and only if, let's see, an minus 1 plus 1 over 4 is less than or equal to an minus 1. And this is true if and only if, I'll bring the 4 over, you get 1/3 is less than or equal to an minus 1. Okay, so it turns out that it's not always decreasing, because it might be increasing if we started with a number bigger than 1/3. Okay? On the other hand, our initial value is greater than 1/3, so it will turn out to be a decreasing sequence. So it'll turn out that if I started with like A1 to be a 1/6, what you can check is that this is going to be monotonically increasing up to 1/3 as well. Okay? So let me just, we still have to show this. Okay, so this is like proof by induction. And the statement I want to make is that I want to prove that 1/3 is less than or equal to an, which is less than or equal to an minus 1 for all n. Okay, and this will obviously show that it's a monotonically decreasing sequence. Okay, so n equals 2, I guess, can be our base case. And this is okay, right? Because we showed 1/3 is less than or equal to 2, less than or equal to 7. So now assume that we have this. Or maybe I'll substitute this for k, ak minus 1. And then you want to show that ak plus, that this is satisfied. Okay? Well, and then this is going to be essentially the same computation. So ak plus 1 is equal to ak plus 1 over 4. Since ak is greater than or equal to 1/3, we have ak plus 1 is greater than or equal to 1/3 plus 1 over 4, which is precisely 1/3. Okay? And by the same argument that we did above, since ak is greater than or equal to 1/3, we have that ak plus 1 over 4 is less than or equal to ak, and this is ak plus 1. Okay? So since we have this assumption, or we proved, we're assuming that an is bounded between here. We're able to show the same thing here. Right, so we showed this, and therefore we're done. So therefore it's monotonically decreasing. Now for bounded, as you can guess, the limit of this sequence actually will end up being a third. Okay, so again, you can prove by induction that the ANs are bounded. Maybe I'll just say, I don't know, let's just show that if A sub k is less than or equal to 1, then A sub k plus 1 is less than or equal to 1. All right? And this is because this is AK plus 1 over 4, which is less than or equal to 1 plus 1 over 4, which is a half, so less than 1. All right, and then, it will turn out that A3, I think, is less than or equal to 1, and therefore all of the terms have to be bounded above by 1. Okay, so that's it. And then if you want to show it converges, so we've shown it converges. So convergent by MCT. To show the limit, you just solve that A is equal to A plus 1 over 4, and you get, as we suspected, that the limit has to be 1/3. Okay? All right, so let me go on to 6, which was to show by the definition, so show from the definition that A sub n, which is square root of n over square root of 1 plus n squared, is convergent. Okay? So if you want to show that this is convergent, in this case, you just have to figure out what the limit is supposed to be. Okay? I mean, that's essentially, you just have to make the right guess and then prove from the definition that you made the right guess. Okay? So notice here that square root of 1 plus n squared is very close to n, okay? Or I guess I should say absolute value of n. Right? Though I am assuming here that n is a natural number. So the guess is that, well, A sub n is close to 1 over square root of n, which goes to 0, okay? Which again, we'll show by the definition. Okay, so therefore what we should try to show, okay, so we will show that there exists some n in n so that the absolute value of our terms in our sequence is less than epsilon for all n greater than or equal to n. Okay, so first we can get rid of the absolute value because this is just a positive number for all n. We also know that this is less than or equal to root n over root n squared, which is less than or which is equal to 1 over root n for all n. Okay? Now, what we can say is, well, so what we really need to find is, so since epsilon is greater than 0, epsilon squared is greater than 0, and there exists some n in n, some n in n, so that 1 over n is less than epsilon squared for all n greater than or equal to n. Okay? But now, I claim this works, right? So if 1 over n is less than epsilon squared, then 1 over root n is less than epsilon, and therefore this n that we've chosen satisfies our equation here, right? Since this was bounded by this, and therefore this was less than epsilon. Okay, so let me go to number 7, which was, suppose we have a sequence which is convergent, n equals 1 when it is convergent. And what we had to show is that the sequence b sub n, which was the max of the a sub n's, oh sorry, I should put this here, max of a1 up through an, this is also convergent. Okay, so this one I think is a little trickier than the previous one. So let me just give you some examples before going through the the proof. So let's just say a sub n is our favorite sequence 1 over n. Okay, so a half, a third, or 1, a half, a third, a fourth, and so on. Well, what's b sub n? It's just 1, 1, 1, and so on, right? Because every time you're taking the max of the previous terms, and the maximum is just 1. Okay, so in particular, the limit of the a sub n's does not have to equal the limit of the b sub n's. On the other hand, it can, right? If I did this with an is negative 1 over n, then I would just get bn is an, okay? Because in that case, the largest value is just the nth term. So what can happen here is that, in both cases, you'll get that it's a convergent sequence, but the bn's might converge to something different, or they might converge to the same term. Okay? So again, it will turn out, so since we don't know the limit, we should use monotone convergence theorem. Okay? In this case, actually, I think you can work out, there are a couple of cases, but you can try to work out what the limit is precisely, given that you know the limit of the a sub n's. But the monotone convergence theorem is certainly the simplest way to do this. Okay, so let's just show, well, that so you have to show monotone and bounded. Okay? So the first one, so monotone, is luckily quite easy, right? So since the max of a1 up through ak is strictly less than the max of a1 up through ak plus 1, we must have that the b sub k's, well, are monotonic, right? So we're just taking the max of more and more values every time. So you can only, it might stay the same, or it will just increase, okay? So that's simple. And now for bounded, well, what do we have to show? Well, we know that convergent sequences are bounded. So maybe I'll just I'll just kind of do this again. So an approaches a, okay? So we know there is some n in n, so that a sub n minus a is less than, say, 1 for all n bigger than n. Okay, so I'm just choosing a very specific epsilon. Then the b's, bk, I claim are bounded by, well, they're bounded by the max of a plus 1 and then all the other terms. So a1, a2, up through an. Okay? So here we know, so what could happen is we have our sequence which is converging to A. It might look like this, right, and converge up to A, in which case a plus 1 is a bound. Or, you know, it might have taken A and it might have done some crazy things before eventually getting sucked into the, you know, a minus 1, a plus 1 neighborhood. Okay? So in any case, this is just, you know, a finite list of terms. So this might be like some a sub k up here, which is the largest. And then that gives me my upper bound. Okay? So it's either a plus 1, because everything is eventually in that neighborhood, or you might have, you know, gotten large before then. Okay? Okay, so that is that one. And then finally we have 8, which is let Fn be the Fibonacci sequence. Okay, so we have F1 is 1, F2 is 1, and I think, I hope this came out better on your PDF than my PDF. My Canvas is a little weird. Fn plus 1 is Fn plus Fn minus 1 for n greater than or equal to 2. Okay? And then you want to show that the differences, so Fn over Fn minus 1, converge. Okay? So Xn, and suppose that the xn's go to x, and we have to carefully determine the value of x. Okay, so determine x. So what we want to write is that we know that the limit of the xn's is the same as the limit of the xn plus 1's, okay, which is x. So now we just try to write this down, and you want to write down xn plus 1, hopefully in terms of xn, and then solve for x. Okay, so we want to write down xn in terms of xn, well, I'll say maybe write down xn plus 1 in terms of xn, okay? Sorry, getting sloppy at the end. Or maybe I was sloppy the whole video. Okay, so this is what we want to do, okay? And then use our algebraic trick, okay? So let's just write down xn plus 1. This is fn plus 1 over fn. Oops, sorry, just over fn. Which is fn plus fn minus 1, by definition, over fn, which is 1 plus fn minus 1 over fn. Okay. This term, if it was flipped, it would just be xn. So we get that xn plus 1 is 1 plus 1 over xn. And now we can use our algebraic trick, right? So if we know that this converges to x and this converges to x, then x has to satisfy x is 1 plus 1 over x. So therefore we get x minus 1 is 1 over x squared minus x is 1. So we get x squared minus x minus 1 is 0. Okay? And now, quadratic formula says that this is 1 plus or minus square root of 5 over 2. Okay, so golden ratio. Except that we have to be a little more careful, right? Because it's not plus or minus. Since all of these terms are positive, we actually get 1 plus square root of 5 over 2. Okay, so let me just write that out a little bit because it is, we want to carefully determine it. So since the Fn and Fn minus 1 are positive, we must have the limit, so we must have that xn's are positive, okay, since dividing positives by positives gives you a positive. Therefore, the limit has to be positive if it converges, okay? So limit is greater than 0. And on the other hand, 1 minus square root of 5 over 2 is negative, so this is the limit. Okay, so I'm going to stop there. Thanks.